Let's think about the opening question again. What comes to mind when you think about nuclear power? Chances are you reflected on negative thoughts. This is largely because of the tragedies that have transpired from nuclear power. In particular, most people think about the risk of nuclear meltdown like Chernobyl. Chernobyl's in the Ukraine, which is right next to Russia. On April 26, 1986, Reactor 4 at the Chernobyl nuclear power plant, 100 kilometers north of Kiev, blew up during a routine daily operation. Nearly 9 tons of radioactive material, 100 times greater than the Hiroshima bomb, were hurled into the sky. Winds over the following days, mostly blowing north and west, carried fallout into Belarus, as well as Russia, Poland, and the Baltic region in Scandinavia. Control rods were made of graphite, unlike those used in the U.S., which caught on fire. While performing a safety test on Reactor 4, technicians allowed a power surge that reached 120 times the rated capacity of the reactor. The surge, or slow nuclear explosion, ripped open the core, including cooling water pipes, and caused a huge steam explosion. The 4,000-ton concrete covering over the reactor was blown away. Fires broke out in many places all over the site. 50 different radioactive isotopes were released, with half-lives spanning from 2 hours to 24,000 years. These isotopes were shot 1.5 miles into the sky. Over 1,000 injuries and 31 deaths of firefighters and others who reported to the scene of the accident. 150,000 people evacuated from the Ukraine homes. Radioactive cloud released over a large part of Europe. Health-threatening levels of radioactive materials were found in at least 20 nations, and as far away as 2,000 kilometers from Chernobyl. Estimated 250 million people were exposed to unhealthy amounts of radiation. Estimates of future cancers from the accident range from 7,500 to 1 million. Radioactive particles in the environment and in the food chain. Large amounts of uncertainty and fear engulfed the population. The people began to distrust the government. There was a Soviet Union cover-up, with Sweden and Poland were the first nations to bring attention to the accident. Other nations attempted to downplay the health effects of the accident in their own nations. Then the public opposition to building additional nuclear power plants increased significantly worldwide. To this date, only authorized personnel are allowed near the nuclear power plant. The area is still feeling the effects of the radiation. A thick concrete wall was built around the reactor that experienced the meltdown. In the U.S., all the reactors must have a structure surround them to contain all the radioactive material if a tragedy were to happen. This is how scientists and engineers are confident that the same tragedy would not occur here. Nuclear radiation can cause several physiological issues. For instance, it can cause the thyroid to malfunction, which is what regulates your metabolism. Some have had to get it removed as a result of radiation. Radiation sickness is an illness resulting from a large exposure of radiation. The early symptoms can involve anemia, nausea, malaise, and susceptibility to infection. Considerable care has now been taken to protect those who work around radiation, such as protective lead shields. This chart explains some of the effects of radiation. SV here is the international unit for the measure of radiation. is equivalent to 100 rem, which is right here, which is the amount of radiation received that takes into account the damage to the human tissue. This can be broken down to the type of radiation, the type of tissue, the rate at which it was delivered. Was it extremely mild or for a long period of time, or very sudden? Notice that there are no observable effects in very low dosages. At 0.25 SV, this is 70 times more than the average person gets. So the average person is exposed to radiation on a regular basis, but there are no effects because the amount is so small. However, if a tragedy were to occur, obviously more effects will be noticed. Speaking of tragedy, what about nuclear energy is used in bombs? The isotope U-235, which means uranium with a mass of 235 and 238, behave essentially the same in all chemical reactions. So the separation of the two isotopes is extremely difficult and relies on advanced technology that is not readily available. Building and deploying nuclear radiations is a very difficult operation to carry out. To get the fuel necessary for the power plants and for the weapons are very similar. This nuclear fuel cycle simplifies the very complex procedure. Initially, the uranium is drilled. This is a mineral ore that contains UO3, uranium trioxide, or uranium dioxide. This is then reacted to create UF6, uranium hexafluoride, because it is easier to work with. Once UF6 has been made, it can be separated into two isotopes of uranium, 235 and 238. Remember that isotopes are the same elements but different amounts of neutrons. So the 238 has 3 extra neutrons in its nucleus. The U-235 is more radioactive. So it is the desired isotope. From here, the U-235 compound is further processed into fuel rods, used as fuel, and then stored and disposed of. This is an awesome source of electrical energy. But what to do with the spent nuclear fuel? Each radioisotope has its own half-life. Some half-lives are only fractions of a second, while others last hundreds of thousands of years. The half-life is the time required for the radioactivity to fall to 1/2 of its initial value. So if it starts at 100, at its first half-life it'll be 50%. The next half-life it'll be 25%, and so on. Notice that there's a huge range in half-lives. Uranium-238, which is right here, has a half-life of 4.5 times 10 to the 9th, while uranium-235 has 7.0 times 10 to the 8th. Remember, this 9 here is how many places you move the decimal. So it's 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. I moved the decimal place 9 times when I did that. 1, 2, 3, 4, 5, 6, 7, 8. I moved the decimal 8 places when I did that. And that's years. That's how many years it takes for it to break down. Another example is carbon-14. This is used for what's called carbon dating, that you may have heard of. This half-life is 5,715 years old. This is where the controversy of carbon dating lies. Those who oppose carbon dating state that the time frame is entirely too large to be accurate. However, scientists are using it to measure things that are 100,000 years old, so it's actually relatively off by about 10%. As you learned in the previous slide, uranium-238 has a half-life of 700 million years. So what do we do while we're waiting for it to decompose? There are two different kinds of nuclear waste: high-level radioactive waste and low-level radioactive waste. Low-level radioactive waste are smaller quantities of safer compounds, such as nuclear medical waste. High-level radioactive waste consists of materials that were never decomposed and are found in extremely dangerous conditions. Unused nuclear weapons would be an example of these. Within this category is the spent nuclear fuel that was used in power plants. In each power plant, about 30% of the fuel rods are replaced annually. For the first year or two, the spent rods are transferred to pools of water. So this is like a big swimming pool of water that they're sitting in. They are then dried and transferred to a dry cask storage in leak-proof containers. Some plants choose to vitrify their waste, which means they encase it in glass to prevent leakage. It's just one extra safety precaution. However they decide to encapsulate it, the final disposal must be determined. The final step of nuclear waste is to decide what the burying ground will be. One option is for storage on or near the surface of the earth. That's this one right here. If this is the choice, society is making a commitment to monitor it for thousands of years. The other option is to bury the waste. It still needs to be retrievable, but it is done with the intent of little human interaction. This seems to be the more favorable, with the fear that future generations will forget about the waste and it causing more harm at the surface. It has been proposed to deposit the waste in the Yucca Mountains. Some believe that the waste may re-enter the earth as part of the ore once again. Only thousands of years of time will tell this will be true. The controversy continues. Which is better, coal or nuclear? Which is better for the environment? Which is better for society? Which is better for business? Think about these questions. You have all the facts now. What do you think?